Hello, welcome back to Digital Aurum. In the first part, we learned what SUID is and why it is one of the most important special permissions in Linux. We saw that SUID allows a program to run with the permissions of the file owner, not necessarily with the permissions of the user who executes it. We also learned that if an SUID program is owned by root and contains a vulnerability, the impact can be very serious because that program may perform actions with elevated privileges. We also saw that SUID is represented in octal notation with a 4 at the beginning, as in 4755. We learned that in the output of ls-l, SUID appears as an S in the position where the owner's X would normally appear. For example, -rwx-x-x. Now we are going to continue with the other two special permissions, SGID and Sticky Bit. These two permissions are different from SUID, but they are also very important for understanding how Linux controls groups, shared directories, and security between multiple users. Let's start with SGID. SGID means Set Group ID. The main idea behind SGID is similar to SUID, but instead of working with the file owner, it works with the file's group owner. When SGID is applied to an executable file, that file can run with the permissions of the group owner. In other words, the program can run inside the context of the group associated with the file. This can be useful when several users need to run a tool with permissions related to a specific group without giving them full control of the system. But SGID also has a very important use in directories, and this is probably the most common use in system administration. When SGID is enabled on a directory, new files created inside that directory can inherit the group of the directory. But there is one more important detail. It is not only new files. New subdirectories created inside that directory can also inherit the same group, and they can also inherit the SGID bit, so the collaboration chain does not break. Imagine a shared folder for a team. For example, a team of administrators, developers, or security analysts. Everyone needs to create files and folders inside the same shared location. But you want those files and folders to keep the same group, so the team can collaborate without breaking permissions every time someone creates something new. That is where SGID helps. It allows files and subdirectories created inside that directory to keep the directory's group. This creates consistency, and from an administration point of view, it can be very useful. But from a cybersecurity point of view, it must be configured carefully. Because if a directory with SGID has permissions that are too open, unauthorized users may be able to create or modify files inside a group context that has more access than necessary. When used correctly, SGID helps organize permissions. When used incorrectly, it can expand access beyond what was intended. Now let's connect SGID with octal notation. In special permissions, SGID has the value 2. That means if we see a permission like 2755, that initial 2 tells us that SGID is enabled, and the other three numbers, 755, represent the normal permissions of the file or directory. Just as 4755 indicates SUID, 2755 indicates SGID. This fourth digit at the beginning is important because it changes the meaning of the permission. Now, how does SGID appear in the output of ls-l? Normally, we may see permissions like -rwx-r-x, r-x. But when SGID is enabled, we will see an S in the position where the group's X would normally appear. For example, -rwx r-s r-x. Look at the group section, r-s. That S indicates that SGID is enabled. If the S is lowercase, it means SGID is enabled and the execute permission for the group is also present. But if we see an uppercase S, it means SGID is enabled, but the execute permission for the group is missing. That may indicate a strange configuration or something that requires review. Once again, a single letter can completely change how we interpret the permission. Now let's move to the third special permission, Sticky Bit. Sticky Bit is mainly used on shared directories. Its purpose is to protect files inside a directory where multiple users can write. The classic example in Linux is /tmp. The /tmp directory is a temporary location where many users and processes can create files. But this creates an important security question. If many users can write inside the same directory, what prevents one user from deleting another user's files? That is where Sticky Bit comes in. When a directory has Sticky Bit enabled, users can create files inside that directory, but normally they can only delete their own files. Unless you are the administrator, root, or the owner of the directory, you cannot delete other users' files simply because the directory is shared. This is extremely important because it allows many users to use a common directory without allowing anyone to destroy files that belong to someone else. In other words, Sticky Bit allows shared access, but with protection. Now let's connect Sticky Bit with octal notation. Sticky Bit has the value 1. That is why when we see a permission like 1777, that initial 1 tells us that Sticky Bit is enabled. And the other 3 numbers, 777, represent broad normal permissions. This case is very important because a directory with permissions 777 allows everyone to read, write, and enter. But if it also has Sticky Bit, as in 1777, users cannot delete files that do not belong to them unless they are root or the directory owner. That is why /tmp normally uses behavior like this. It allows many users and processes to create temporary files, but it prevents one user from deleting another user's files. Now, how does Sticky Bit appear in the terminal? When we run ls-ld/tmp, we may see something like drw-rwx-rwt. Let's read it carefully. The D at the beginning indicates that it is a directory. Then we see broad permissions for the owner, the group, and others. But at the end, we see a T. That T indicates that Sticky Bit is enabled. Here is another important technical detail. If we see a lowercase t, it means Sticky Bit is enabled and the execute permission for others is also present. But if we see an uppercase t, it means Sticky Bit is enabled, but the execute permission for others is missing. And as we learned before, in directories, the execute permission means the ability to enter or traverse the directory. So an uppercase T may indicate a configuration that requires review. Now let's connect everything with the mindset of an analyst. SUID, SGID, and Sticky Bit are not bad by themselves. They are legitimate Linux mechanisms. The problem appears when they are misconfigured, when they appear in places where they should not be, or when they are combined with permissions that are too open. For example, a directory with SGID where unauthorized users can write, a shared folder without Sticky Bit, a temporary directory that is misconfigured, a file or subdirectory inheriting a sensitive group when it should not, or special permissions added without a clear reason. An analyst does not panic just because they see an S or a T. An analyst asks, does this special permission make sense here? Who owns it? What group is assigned? Who can write inside this directory? Do new files and subdirectories inherit a sensitive group? Is this directory shared? Is it protected with Sticky Bit? Are there users who can modify files that are later used by other processes? These questions are important because they help distinguish a normal configuration from a risky configuration. For example, seeing Sticky Bit on /temp is normal, but seeing a shared directory with broad permissions and no Sticky Bit may be concerning. Seeing SGID on a team collaboration folder may make sense, but seeing SGID in a sensitive location with open write permissions may require investigation. The key is not just memorizing symbols. The key is understanding the context, because in cybersecurity, context changes everything. Now, let's summarize clearly. SGID means set group ID. On executable files, it can make a program run with the context of the group owner. On directories, it helps new files and subdirectories inherit the group of the directory. In octal notation, SGID has the value 2, So a permission like 2755 indicates that SGID is enabled. In ls-l, SGID is represented with an S in the group execute position, as in -rwxr-sr-x. Sticky Bit is mainly used on shared directories. It allows multiple users to create files, but it prevents users from deleting files they do not own, unless they are root or the directory owner. In octal notation, Sticky Bit has the value 1, so a permission like 1777 indicates that Sticky Bit is enabled. And in the permission output, it appears as a T at the end, as in drwx-rwx-rwt. These special permissions are a normal part of Linux, but for a cybersecurity analyst, they are signals that must be interpreted carefully. They do not always indicate a problem, but they always require context. In the next video, we will continue moving deeper into operating systems. We will study processes, services, and scheduled tasks, because understanding permissions is fundamental, but you also need to understand what is running on the system, who is running it, and with what privileges. That will be the next step toward thinking like a real analyst. Understand, defend, grow.